Okay, so again, just to reiterate everything we are doing for today, so we are continuing to look at fundamental theorem of calculus. What you want to do is get the example 3 handout out I gave you yesterday. You want example 5 from posting about memes. It's the very next example in there. So we're going to look at lions, tigers, and bears. Oh my. And then you also want the fundamental theorem of calculus packet I gave you that had the mean value theorem, fundamental theorem, and some examples on that front page. So we can go through and work through some of those problems as well. So I'm going to work through some of the examples with you. And then, like I said, put you into breakouts and give you some time and opportunities to really sort of delve into and work through some of these problems on your own. So for all my Irish-blooded kids out there, happy St. Patrick's Day. Hope you're in your green. Hope you have some chocolate or Lucky Charms, and we will get started. So let's start with example 5. Let's start with the lions and tigers and bears. Oh my. So for example 5, you are going to need or want to have a graphing calculator with you, because you can see, as indicated on that image, this is a graphing calculator problem. So, take a minute and read through the top of that example. And as I'm reading through examples like this, what I like to do is really try to pull out or identify the key pieces of information. So for me, one of the things I'm noticing or paying attention to is that we are talking about times on a clock, not change in hours. So it tells me that at t equals 0, that represents 8 a.m. So 0 doesn't represent midnight in this case, it represents 8 a.m. So for part A, where it says how many people have entered the zoo at 12 p.m., I need to take into account that that's representative of 4 hours after 8 a.m. And I'm not integrating from 8 to 12, but rather 0 to 4. So as an integral, this would be 0 to 4 of the function for people entering the zoo. So that's e of t dt. And then at this point, it's all calculator now. So you're going to go to your graphing calculator. Since I have 2 functions, the first thing I'm going to do is list both of my functions in y equals. And make sure my calculator is in radian mode. So I have e of t in y1, and I have L of t in y2. So sometimes on the test, I just make note of that to myself so that as I'm working through my problems, I'm like, oh yeah, y1 is e of t. So really, when I'm integrating this, I'm just going to go to my calculator. And again, this calculator is a little bit older. Some of you might have this calculator. It doesn't have the integral like the calculator we were using in math. So like my integration on here looks a little different. So I'm integrating the function y1 for variable x from 0 to 4. If you're using the newer calculators, you actually just enter all of that in to look like this. And you're going to hit enter. And we see that how many people have entered the zoo by 12 p.m.? Approximately 203.068. This one does not ask me to round to the nearest whole number, so I'm going to write it out as a decimal. I'm going to make sure my decimal has 3 decimal places because we want to incorporate all of those. Okay, part B, 20% of those people who leave the zoo are selected at random to receive a special discount ticket for a return trip to the zoo. How many people have received a discount ticket by 5 p.m.? So people who have left the zoo is represented by L of t. So again, 8 a.m. to 5 p.m. would be 0 to 9 of L of t dt. So that would represent the amount of people who have left the zoo by 5 p.m. If 20% receive a discount ticket, then what we want to do is multiply the amount that have left by 20%, or 0.2. So 0.2, math 9. This time we're looking at vars 2, or function 2, and integrating with respect to variable x from 0 to 9. So we get approximately 79.180 people will be selected to receive a special discount ticket. We now have the introduction of a new function. We have the introduction of function n. N of t represents the amount of people in the zoo, taking into account those who have entered and those who have exited. So n of t represents the amount of people in the zoo, taking into account those who've entered and exited over a 12-hour day. We want to find the value of n10. So again, just even writing out n10 equals the integral from 0 to 10 of e of x minus L of x dx. So I'm going to find what n of 10 represents. So n of 10 in terms of our graphing calculators would be math 9, function y1 from 0 to 10 minus math 9 y2 from 0 to 10. And again, if you have the newer graphing calculator, you can actually do one integral 0 to 10 y1 minus y2 right in that parenthesis area. I just left mine on my desk at school, so and we get 273.635. And that's people, because it's the rate of people entering and the rate of people exiting per hour being integrated, which takes me to people. If I want to find n prime of 10, well, now n prime of 10 would represent the rate of change of people in the zoo. So if you take the derivative of the integral, you're just left with your functions. So that's like e of 10 minus L of 10. And again, I could just go to a table and type in 10, and I'd get 112. So what that means is that negative 6.22 8 people per hour. So the rate of change is negative. So if the derivative is negative, then that means that the amount of visitors in the zoo is decreasing at that time. So n prime of 10, because it says explain the meaning. So the meaning of n prime of 10 means that the number of visitors in the zoo is decreasing by 6.228 people per hour at time t equals 10, or at 6 p.m. And in terms of the previous example, this means that at 6 p.m. there are 273.635 people in the zoo. Part D, at what time t does the model predict the number of people in the zoo is at a max? So again, if you think about maximizing a function, we need to take into account the people entering and exiting. So in order to maximize the function, we're going to look at when the derivative of the people entering and exiting is equal to 0. So that's like looking at n prime of t equal to 0. And we said that n prime of t was equal to e of t minus L of t. So we want to know when e of t equals L of t, because that will be the point at which the max people have entered and max people are exiting. So we entered E and L in my Y1 and Y2. And we know that the amount of people in the zoo is in the hundreds. We know my time is 0 to 12. So I'm going to change my windows, X min and X max, to be 0 and 12. And then I'm going to change my people in the zoo to be between 100 and 300. I'm going to change my Y scale to be 25, just so it doesn't try to do so many tick marks. Oops. So let's make my y's less. So again, if you do what I did, I kind of guessed what I thought I should make my window, and then my window didn't work out so well, so I changed it again. And it looks like my graph hits here, and my graph hits here. So we're going to go to second trace, we're going to go to intersect, and because I can't quite tell if they intersect down here, I'm going to try and guess, just so that I don't miss a point. So I know my x's aren't going to be negative, so I'm going to get really, really close to x over here and do my guess. And I see that they do intersect at negative 0.008. So what that means is within the first hour of the zoo opening, there is a potential max number of people. So this is our candidates test. So really what we're doing is comparing the time and the amount of people. So we want to compare time point 008. We're going to compare the next point of intersection, and just so I don't have to scroll all the way over, I'm going to type in like x equals 10 to try to move my cursor over there. Then I'm going to go to intersect, and I'm going to move my closer and closer. And I see that the second point of intersection is at 8.134. And then we know the last point of intersection is going to be 12 when the zoo closes. So how many people are there at the end of the day? Now, you could include 0, but we should know that at time t equals 0, there are no people leaving and there are no people entering, because time t equals 0 would look like the integral from 0 to 0 of e of t dt minus the integral from 0 to 0 of L of t dt. So we know any integral that goes to the same bound is 0. And again, be careful when we do our table to find that model of people. We're looking at n of t, not n prime. So to find this value here for 0.008, I'm looking at the integral from 0 to 0.008 of e of t minus L of t dt. So to do that on my calculator, I'm just going to go back. I'm going to go to Math 9. And again, I was telling you before, you could do vars, y vars function, y1 minus vars, y vars function, y2. From x to 0 to 0.008. And we get a negative 0.002. So what that means is that the approximate number of people in the zoo is at a negative. So that is probably the minimum value, not the maximum. And then we're going to take that same thing, our same values, and we're going to now change our bounds to be 0 to 8.134. And I get 281.11. And then we're also going to take that same thing and we're going to look at it at hour 12. And we get 260.905. So this is what we call that candidates test for extreme values, and essentially what we have done is found the endpoints, and we found the min and the absolute max inside as potentials. So these are from our candidates test. Those are called critical points. And what we can say is that the max number of people in the park is approximately 281 at time 8.134 hours. Okay, so that is a rate in and rate out. I can pretty much guarantee you will see a question like that on your mock exam, on your AP test, etc. So that's why we're really focusing on that this week. That's why there's so many practice problems having to deal with that for today. That's why yesterday I kind of said, hey, like you might want to look at the fundamental of theorem homework handout that we're still going to do some problems with together as a group, but you know, ultimately these are questions that we have the skill sets to solve. It just takes practice. And the more practice you do, the better you're going to get, the more you're going to be able to interpret those questions. So one of the things I noticed on our 5.1 to 5.3 quiz, and I've brought it up previously in class, was that we were under the impression that if a function had discontinuity, it wasn't able to be integrated. And I want to show you through this example here that that's not the case. It's just that if a function is continuous, it is guaranteed to be integratable. Just because it's a piecewise doesn't mean it isn't integratable. So we are asked in this example to evaluate the integral from 0 to 5 of f of x dx, where f of x is represented by this piecewise function. So when you graph this from 0 to 3, it applies this function right here. So it goes through 1, 2, 3, 4, 5, 6, 7. And then it has a slope of -2, so it's going down 2 and over 1, all the way to 0.3. And then we have this second function over here that starts at 4 and continues indefinitely. So we have this piecewise function, and it has discontinuity. It has discontinuity at 0.3. So this is not a continuous function. However, the area under the curve of this function does exist. The area under the curve from here to here can be represented by the integral from 0 to 3 of -2x plus 7 dx. So the integral from 0 to 5 of f of x dx would equal the integral from 0 to 3 plus the integral from 3 to 5 of 4 dx, which would be the area under this curve here. Whoops, too far. So you have a triangular trapezoid, because that little piece right there doesn't go all the way to the bottom, and a rectangle whose areas are being added together. So just because there's that discontinuity doesn't mean you can't find the area under the curve. And that was something we really needed to understand. So you can take the antiderivative of each of these algebraically. You could find the areas geometrically. So this would be like negative 2x squared over 2 plus 7x from 3 to 0 plus 4x from 5 to 3. And you'd have negative x squared plus 7x from 3 to 0 plus 4x from 5 to 3. Plugging in your upper and lower bounds, you'd have negative 9 plus 21 minus 0 plus 4 times 5, which is 20, minus 4 times 3, which is 12. So 20 and 21 would give you 41, and then 41 minus 12 and negative 9 would really, well, 9 and 12 would be 21, so you'd get 20. Or you could have done it geometrically. So you could have said, okay, this is a trapezoid from 0 to 3. So its area is 1/2 the height, which was 3, and then add up your bases, so 7 and 1. Plus the rectangular space, whose height was 4 and base was 2. So 8 times 1/2 is 4. 4 times 3 is 12. 12 plus 8 is also 20. So I just wanted to go back and reiterate that just because a function has discontinuity does not mean it doesn't have an integrated area under the curve. So that covered example 3, that covered example 5. And then, like I said, I gave you these packets yesterday. I posted it on Fusion and Teams. On Fusion, it's just already attached to the 5-4 fundamental theorem of calculus. And then I sent it on Teams yesterday in the group chat as images because some of you were having trouble finding it. So not a problem. It's there for you. That first page is really just knowledge. The next page is what we're going to work on today using the remainder of class time. So this was the handout I was saying, like, I'm going to do 1, 2, you know, and definitely I want to do 13 with you because it's another related rate and free response question. So what I want to do, though, is just start off with examples 1 so that we can talk about the examples first and then build up to kind of understanding what we need to understand. Okay. So example 1 sort of walks us through everything we need to walk through, but it says, suppose that C of t represents the cost per day to heat an office measured in dollars per day, where t is measured in days, and t of 0 corresponds to January 1st of 2015. If 0 to 60 of C of t and 1 over 60. So we want to interpret, what does that mean? So you have to think about the fact that an integral from 0 to 60 of C of t dt, where C of t represents cost per day. So if you integrate cost per day, then you're left with cost. So the integral from 0 to 60 of C of t dt is going to represent or be equivalent to the cost. And in this case, it represents the total cost for 60 days, because it's 0 to 60, so it represents the total cost in the first 60 days. The second expression is our average value function. So the minute they put the upper minus the lower bounds in front of that integral, it now gave you the average cost per day, because these units here are days. We just said the unit here was cost. So if you take cost and you multiply it by 1 over days, the average value of the function represents the average cost per day, once again, for the first 60 days. So question 2, again, we're just talking about units and what they represent. So it says in question 2, if the volume of water in a tank at time t is represented by V of t. So V of t is volume. So in my head, I'm thinking, okay, volume, volume, volume. The derivative of volume is area. We lose a unit. So volume is inches cubed per time. So then its derivative is inches squared per time. So it loses a unit as we go down. So if we're talking about the integral of volume's derivative, now we're talking back about the original again. So to integrate the derivative, you get back the original. So that would represent the volume in the tank at 2, volume in the tank at time 1. Therefore, it represents the volume in the tank and its change between those two times. If the rate of growth of a population is represented by a derivative, so derivative, rate of growth, then the antiderivative, like what comes first, the original, would represent its increase in population. So again, we're just talking a lot about how to interpret these. So question 4, which is our first real problem now, says if oil leaks from a tank at a rate of R of t dt gallons per minute, what does the integral from 0 to 180 of R of t dt represent? So if R of t is gallons per minute, and we integrate that, then that means that this represents the number of gallons of oil